Hello, and welcome to Sleepy Universe. Whatever day you've had, you can let it go now. There is nothing you need to do, nothing you need to solve. Tonight, we'll take a gentle journey through the cosmos itself. We'll explore 100 quiet facts about space, time, and the vast silent mysteries that fill the universe. You don't need to remember any of them. Your only task is to listen and let your mind drift among the stars and galaxies. So, find a comfortable position. Feel your body grow heavy, supported by your bed. Let the weight of the day melt away with each breath. Just listen and imagine we are floating, untethered, in the deep, quiet expanse of space, looking out at the infinite tapestry of creation. Now, let your awareness float up beyond the atmosphere, beyond the moon, and into the peaceful darkness between the stars. Let's begin. The universe is 13.8 billion years old. This number represents a chronology of almost incomprehensible depth, a silent epic written in the slow, unfurling script of cosmic evolution. Within this vast expanse of time, generations of stars have been born from nebulous clouds, lived out their long, luminous lives, and returned their enriched substance to the galactic medium in final, brilliant acts. Entire galaxies have performed their slow, gravitational waltzes, merging and spinning in a darkness punctuated only by their collective light. The sheer scale of this timeline renders all human endeavor a fleeting, gentle whisper against the patient, enduring background hum of the cosmos, a hum that speaks not of urgency, but of a profound and endless becoming. The vacuum of space is a profound and unbroken silence. This silence is the universe's most fundamental state, a perfect acoustic void where no vibration can propagate. The most cataclysmic events, the collapse of a stellar core, the eruption of a solar flare large enough to engulf planets, the slow grinding collision of whole galaxies, all occur in absolute, motionless quiet. It is a silence that is not merely an absence of sound, but a positive presence, a blanket of quiet that smothers the cosmos. This pervasive hush is a reminder that the universe's most powerful forces operate in a realm of deep, resonant peace, where the frantic noise of earthly existence has no place and no meaning. Human bodies are composed of elements forged in stellar furnaces. The very substance of life is a testament to cosmic recycling on a grand scale. Every atom of carbon, every nucleus of iron, every particle of oxygen that constitutes our physical form was once part of a star that no longer exists. These elements were synthesized in the intense heat and pressure of stellar cores, during the stable burning of a star's life, or in the violent throes of its supernova death. Scattered across light years by these explosive events, this cosmic debris eventually coalesced within a molecular cloud that would form our solar system. We are, therefore, not just observers of the cosmos, but literal embodiments of its ancient history, walking archives of long-dead suns. The number of stars exceeds all the grains of sand on Earth. The abundance of stellar bodies in the observable universe is a figure that transcends human scales of counting. To visualize it requires contemplating every single grain of sand, on every beach, in every desert, and in every riverbed across our entire planet. Then, one must understand that the number of stars, each a potential sun, many harboring their own systems of worlds, dwarfs this earthly total by an almost unimaginable factor. This statistic paints a portrait of a cosmos that is not sparse or lonely, but one of overwhelming, vibrant richness. It is a universe teeming with potential, a silent, glittering tapestry of such density that the very concept of emptiness loses its meaning. A day on Venus lasts longer than its year. The rotational rhythm of Venus is a study in celestial languor. The planet completes a single, slow turn on its axis over a period of 243 Earth days, a gradual spin that makes the sun's passage across its cloudy sky an achingly slow event. Meanwhile, its journey around the sun, its orbital year, is completed in a shorter span of 225 Earth days. This creates a world where the definitions of day and year are inverted, where a sunrise is a rare celestial occurrence, and where the passage of time itself feels stretched, distorted, and deeply tranquil. The atmosphere of Venus is a thick, swirling cloak that further muffles the world, contributing to its sense of perpetual, sleepy twilight. The pillars of creation are stellar nurseries of gas and dust. These iconic structures residing within the Eagle Nebula are monuments to the slow, creative forces of the universe. They are not solid, but incredibly vast and tenuous clouds of cold molecular hydrogen and dust, sculpted over millennia by the intense radiation from nearby massive newborn stars. Their majestic, pillar-like forms are actually evaporating, the material being slowly boiled away into space, a process that ironically triggers the birth of new stars within them. Dense knots of gas, shielded deep within these dark columns, collapse under their own gravity, gradually heating up until nuclear fusion ignites in their cores. These pillars are thus both cradles and tombs, sites of simultaneous creation and dissolution on a timescale of millions of years. Dark matter is the unseen architecture of the cosmos. This mysterious form of matter comprises the vast majority of the gravitational material in the universe, yet it reveals itself only through its subtle influence on the things we can see. It does not interact with light in any way. It neither emits, absorbs, nor reflects it, rendering it completely transparent and invisible. Its presence is inferred from the way it bends space-time, guiding the rotational speeds of galaxies and shaping the largest structures in the universe, the great cosmic web of filaments and voids. Dark matter is the hidden skeleton upon which the visible universe is draped, a silent, pervasive framework that dictates the motion of galaxies and the fate of the cosmos, all while remaining eternally in the shadows. The present moment is fluid across cosmic distances. The finite speed of light ensures that all astronomical observation is an act of looking into the past. When gazing at the moon, we see it as it was over a second ago. Viewing the sun reveals an image from 8 minutes in the past. The light from the nearby Andromeda galaxy is a 2.5 million-year-old relic, and the photons from the most distant quasars have been traveling for over 12 billion years, showing us the universe in its infancy. This means there is no single universal now. The cosmic present is a fragmented concept, a personal and localized experience. The sky is a mosaic of different historical epochs, all superimposed into a single, silent, nocturnal display. Brown dwarfs are failed stars that glow with faint warmth, occupying the mysterious gap between giant planets and small stars. Brown dwarfs are celestial objects that formed like stars, but lack the critical mass to sustain hydrogen fusion in their cores. They are sometimes called failed stars. Without a stable internal energy source, they do not shine with the brilliant, steady light of a true star. Instead, they radiate a deep residual heat from their initial gravitational collapse, glowing faintly in infrared light. They spend billions of years in a long, slow cooling process, fading gradually into the darkness. These solitary, warm orbs wander the galaxy as dim, ruddy ghosts, their quiet existence a testament to a path of gentle warmth over brilliant nuclear fire. Empty space is a sea of quantum potential. The vacuum of space, once thought to be a true void, is now understood to be a vibrant, dynamic arena. At the quantum level, it is a seething foam of virtual particles that spontaneously pop in and out of existence, borrowing energy from the fabric of space-time itself for fleeting moments. This constant, low-level activity is governed by fundamental quantum fields that permeate all of reality, their values fluctuating even in the deepest emptiness. This quantum vacuum is not nothing. It is a fertile ground, a state of minimum energy from which particles can be summoned and into which they can disappear. The apparent calm of the interstellar void is an illusion, masking a bedrock of reality that is endlessly restless and full of latent potential. A neutron star is the unfathomably dense remnant of a supernova explosion. When a massive star reaches the end of its life, its core collapses under its own immense gravity in a matter of seconds. This implosion crushes the protons and electrons together, forming a sphere of almost pure neutrons. The result is an object with the mass of 1 or 2 suns compressed into a city-sized sphere, a density so extreme that a single teaspoon of its material would weigh billions of tons. These objects often spin with incredible velocity, completing multiple rotations every second, and possess magnetic fields trillions of times stronger than Earth's. They are the ultimate expression of gravitational collapse, silent and incredibly dense, relics drifting through the galaxy. Their presence often only betrayed by the rhythmic pulses of radiation, if they happen to be aligned as pulsars. Spiral galaxies do not rotate as solid entities, but exhibit differential rotation. Unlike a spinning disk, where every point moves in lockstep, the stars and gas clouds in a spiral galaxy orbit the galactic center at speeds that depend entirely on their distance from it. Stars closer to the central bulge complete their orbits in a much shorter time than those drifting in the vast, sparse outskirts of the galactic disk. This fundamental characteristic is the very reason spiral arms exist, not as permanent physical structures, but as grand, sweeping density waves. These waves are patterns of compressed gas and enhanced star formation that move through the galactic disk with a stately, slow grace. while individual stars endlessly flow into and out of them, like celestial cars entering and leaving a slow-moving traffic jam on a cosmic freeway. The cosmic web constitutes the largest known pattern in the universe. On the grandest scales, the distribution of matter in the cosmos is not random but forms an intricate web-like structure. This vast architecture consists of enormous filaments of dark matter stretching for hundreds of millions of light years, upon which galaxies are strung like luminous pearls. These filaments intersect at dense nodes, which are home to massive clusters containing thousands of galaxies. Between these brilliant strands of light and matter lie the cosmic voids, immense regions of startling emptiness that can span hundreds of millions of light years across. This magnificent, sprawling web is the result of gravity acting over nearly 14 billion years, a slow, patient process that drew dark matter and gas into this complex, hierarchical structure that defines the skeleton of the observable universe. The cosmological redshift is a fundamental signature of an expanding universe. The light emitted from distant galaxies undergoes a subtle but measurable shift towards the longer, redder wavelengths of the spectrum. This phenomenon, known as redshift, is not due to the galaxies moving through space in a traditional sense, but is a direct consequence of the expansion of the fabric of space-time itself. As the light travels across the cosmic void over millions or billions of years, the space through which it propagates stretches, elongating the light waves and causing this characteristic shift. The degree of redshift is directly proportional to the distance of the galaxy, providing astronomers with a powerful tool for measuring cosmic distances and mapping the history and geometry of the universe's relentless growth. The Oort cloud is a theoretical, distant reservoir of icy planetesimals. Far beyond the orbit of Neptune and the scattered disk of the Kuiper belt, the Sun's gravitational influence is thought to extend to a vast, spherical shell of icy bodies known as the Oort cloud. This distant realm, which may begin nearly 1,000 times farther from the Sun than Earth and extend outward to nearly a light year, is believed to be the source of long-period comets. These comets are pristine, frozen remnants from the solar system's earliest days, and their orbits are occasionally perturbed by the gravitational influence of passing stars or galactic tides, sending them on long, falling journeys into the inner solar system, where they blossom into the spectacular comets that have captivated humanity for millennia. A white dwarf is the glowing, Earth-sized ember of a deceased star. After a star of low to medium mass, like our Sun, exhausts its nuclear fuel, it undergoes a transformation, gently expelling its outer layers into space to form a beautiful, often spherical, planetary nebula. What remains is the star's exposed core, now a white dwarf. This object, composed primarily of carbon and oxygen, contains a sun's worth of mass compressed into a volume no larger than Earth, supported against further collapse by a quantum mechanical effect known as electron degeneracy pressure. No longer capable of fusion, a white dwarf simply radiates its immense residual heat out into the cold of space, embarking on a multi-billion-year journey of gradual cooling and fading, destined to ultimately become a cold, dark, crystalline object known as a black dwarf. Gravitational lensing is the bending of light by massive objects, as predicted by Einstein's theory of general relativity. Mass and energy warp the fabric of space-time. This curvature causes the path of light, which follows the geometry of this warped space-time, to bend when it passes near a massive object like a galaxy or a black hole. This phenomenon, gravitational lensing, can act as a natural telescope, magnifying the light of incredibly distant galaxies that lie behind the foreground mass. It can also create multiple images, distorted arcs, and even complete rings of light, known as Einstein rings, providing astronomers with a powerful tool to study the distribution of both visible and dark matter, and to observe the most distant reaches of the observable universe. The habitable zone defines the orbital region where liquid water could exist. Often referred to as the Goldilocks zone, this is the circumstellar region around a star where the temperature conditions are theoretically just right, not too hot and not too cold, for water to exist in a stable liquid state on the surface of a rocky planet. This concept is a cornerstone of astrobiology, as liquid water is considered an essential ingredient for life as we know it. A planet orbiting too close to its star would suffer a runaway greenhouse effect, boiling away its oceans, while a planet too far would be a frozen, icy world. Our own Earth orbits comfortably within the Sun's habitable zone, a fortunate placement that allowed for the flourishing of its biosphere. The interstellar medium is the tenuous mixture of gas and dust permeating the galaxy. The space between the stars is not a perfect vacuum, but is filled with an extremely diffuse, dynamic medium of gas and dust. This interstellar medium is composed of about 99% gas, primarily hydrogen and helium, and 1% microscopic dust grains of carbon and silicates. It exists in several distinct phases, from cold, dense molecular clouds that are the birthplaces of stars, to warm, neutral atomic hydrogen regions and hot, ionized bubbles carved out by the powerful shockwaves of supernova explosions. This medium is the galactic ecosystem, constantly being enriched by the heavy elements forged in stellar interiors and supernovae, and then recycled into new generations of stars and planetary systems. A pulsar is a highly magnetized, rotating neutron star that emits beams of radiation. When a neutron star is born with a powerful magnetic field that is misaligned with its rotation axis, it can manifest as a pulsar. As the star spins rapidly, sometimes hundreds of times per second, intense beams of radiation stream outward from its magnetic poles. If one of these beams periodically sweeps across Earth's line of sight, astronomers detect a highly regular, pulsating signal across various wavelengths, from radio waves to gamma rays. The precision of these pulses is phenomenal, rivaling atomic clocks, making pulsars exquisite natural laboratories for studying extreme physics and even for the nascent field of gravitational wave astronomy. A star's initial mass is the primary determinant of its life cycle, and ultimate fate. The mass with which a star is born sets it on a specific and unchangeable evolutionary path. Low-mass red dwarfs, the most common stars in the universe, burn their hydrogen fuel with a slow, steady frugality, allowing them to shine for trillions of years. Medium-mass stars, like our Sun, lead stable lives for billions of years before evolving into red giants and ultimately shedding their outer layers to become white dwarfs. In contrast, high-mass stars live fast and die young, consuming their nuclear fuel in just a few million years before ending their lives in cataclysmic supernova explosions that seed the galaxy with heavy elements and leave behind neutron stars or black holes. The event horizon of a black hole is a boundary of no return. This is not a physical surface, but a mathematically defined region in space-time that marks the point of irrevocable gravitational capture. Once any object, or even light itself, crosses this invisible threshold, the escape velocity required to break free exceeds the speed of light. Since nothing in the universe can travel faster than light, crossing the event horizon is a one-way journey into the black hole's interior. It acts as a perfect cosmic veil, forever separating the singularity at the black hole's heart, a point of infinite density where the known laws of physics break down, from the rest of the observable universe. Cosmic inflation was a period of exponential expansion in the universe's earliest moments. In the first tiny fraction of a second following the Big Bang, the universe is theorized to have undergone an incredible exponential growth spurt known as inflation. During this fleeting epoch, the universe expanded by a factor of at least 10 to the 26th power in size. This theory elegantly explains several key features of the observed cosmos, such as its large-scale uniformity, its flat geometry, and the origin of the initial density fluctuations that would later seed the formation of galaxies. Inflation set the initial conditions for the subsequent, more gradual expansion of the universe that continues to this day. The James Webb Space Telescope is a premier observatory for infrared astronomy. Positioned at the stable Lagrange point 2, far from Earth's interfering heat and light, this engineering marvel is designed primarily to observe the universe in infrared light. Its large, segmented, gold-coated mirror is exquisitely sensitive to heat, allowing it to peer through obscuring clouds of cosmic dust to witness the birth of stars and planetary systems. Furthermore, because the light from the most ancient, distant galaxies has been stretched into the infrared part of the spectrum by the cosmological redshift, Webb acts as a powerful time machine, gazing back over 13.5 billion years to see the first galaxies emerging from the cosmic dark ages. The Fermi bubbles are colossal structures of high energy emission emanating from the galactic center. Stretching for approximately 25,000 light-years both above and below the plane of the Milky Way, these gigantic gamma-ray emitting structures were a major, unexpected discovery. They form a distinct hourglass-like shape centered on our galaxy's core. Their origin is believed to be linked to a past period of intense activity from the supermassive black hole Sagittarius A star, or a burst of rapid star formation that occurred several million years ago. These faint, ghostly bubbles are a testament to the dynamic and sometimes violent history of our own galactic home, a lingering echo of a long-ago energetic event. A quasar is the intensely luminous active nucleus of a distant galaxy. Quasars, or quasi-stellar objects, are the most energetically persistent objects in the universe. They are powered by supermassive black holes at the centers of galaxies that are actively accreting immense quantities of gas and dust. As this material spirals inward at near light speeds within an accretion disk, it is heated to temperatures of millions of degrees, releasing staggering amounts of radiation that can outshine the combined light of every star in the host galaxy. These brilliant beacons, visible from the farthest reaches of the cosmos, provide a window into the early universe when such galactic activity was far more common. Our solar system resides in a minor spiral arm known as the Orion Spur. The Sun is not located in one of the Milky Way's major, prominent spiral arms, but in a smaller, partial arm or spur that bridges the gap between the larger Perseus and Sagittarius arms. This relatively quiet suburban location, about 26,000 light-years from the galactic center, may have been a crucial factor for the development and sustainability of life on Earth. It places us in a region with a lower density of massive short-lived stars whose eventual supernova explosions could have been catastrophic for planetary atmospheres, offering a more stable and peaceful environment over cosmic timescales. A supernova can, for a brief period, outshine its entire host galaxy. The catastrophic explosion of a massive star, or the thermonuclear detonation of a white dwarf in a binary system, results in a supernova, one of the most energetic events in the universe. For a few weeks, the light produced by this single event can rival, and even exceed, the combined luminosity of the hundreds of billions of stars in its galaxy. This brilliant, transient flash is a primary cosmic source for the creation and dissemination of heavy elements, such as iron, silver, gold, and uranium, enriching the surrounding interstellar medium and ensuring that future generations of stars and planets will be built from this chemically diverse material. The Moon is in a slow, steady retreat from the Earth. Due to the transfer of angular momentum through tidal interactions, the Moon is gradually moving away from our planet at a rate of approximately 3.8 centimeters per year. This process, which has been precisely measured using laser reflectors left on the lunar surface by Apollo astronauts, is also having a reciprocal effect on Earth. It is very gradually slowing our planet's rotation, lengthening our day by a tiny fraction of a second each century. In the distant past, the Moon was significantly closer, appearing larger in the sky, and Earth's days were considerably shorter, a reminder of the dynamic and evolving nature of celestial mechanics. The speed of light in a vacuum is the ultimate speed limit of the cosmos. At 299,792,458 meters per second, the speed of light is a fundamental constant of nature, a universal speed limit that cannot be exceeded by any object or information. This constancy is a cornerstone of Einstein's theory of special relativity and has profound implications for our understanding of causality, simultaneity, and the very structure of space-time. It is the reason we measure astronomical distances in light years, and why every look at the cosmos is inherently a look into the past, as the light from every star and galaxy carries with it a history of its long journey across the expanding universe. The cosmic distance ladder is the method astronomers use to measure the scale of the universe. This intricate process involves a series of overlapping techniques, each calibrated by the previous one, to reach across vast interstellar and intergalactic distances. It begins with fundamental geometry, using parallax to measure the distances to nearby stars, then progresses to standard candles like Cepheid variable stars, whose known luminosity allows for calculating distances to nearby galaxies. Finally, the redshift of type Ia supernovae and entire galaxies provides the final rungs on this ladder, enabling astronomers to map the universe from our solar neighborhood to the very edge of the observable cosmos, each step building upon the last in a careful, cumulative process of cosmic cartography. A globular cluster is a spherical collection of ancient stars orbiting a galactic core. These magnificent, densely packed structures contain hundreds of thousands to millions of stars gravitationally bound together in a perfect sphere. What makes them particularly remarkable is their incredible age. Most globular clusters are among the oldest objects in their host galaxies, having formed when the universe was young, typically 11 to 13 billion years ago. Their stars are metal poor, meaning they contain very few elements heavier than hydrogen and helium, indicating they formed before multiple generations of supernovae had enriched the interstellar medium. These celestial time capsules orbit in the galactic halo, preserving in their stellar populations a pristine record of the early conditions of galaxy formation. The anthropic principle is the philosophical consideration that the universe's fundamental constants appear finely tuned for life. This observation notes that many of the physical constants governing our universe, the strength of gravity, the nuclear force, the mass of the electron, exist within an extraordinarily narrow range that permits the existence of complex structures, including stars, planets, and life itself. If any of these values were slightly different, atomic nuclei wouldn't form, stars wouldn't burn, or the universe would have collapsed immediately after the Big Bang. While various interpretations exist, from the selection effect of our existence in a hospitable universe to the speculative concept of a multiverse, the anthropic principle highlights the remarkable precision underlying cosmic reality and our particular place within it. A visual binary star system consists of two stars that can be resolved through a telescope. Unlike spectroscopic binaries that require analysis of their combined light, or eclipsing binaries detected through periodic dimming, visual binaries appear as distinct points of light through sufficient telescopic observation. These stellar pairs orbit around a common center of mass, and by carefully tracking their positions over many years or even decades, astronomers can calculate their orbital periods, masses, and other fundamental properties. These systems provide crucial data for understanding stellar evolution and mass luminosity relationships, serving as cosmic laboratories where the principles of orbital mechanics can be directly observed and measured. The heliosphere is the vast, bubble-like region of space dominated by the solar wind. This protective cavity, created by the constant outflow of charged particles from the Sun, extends far beyond the orbit of Pluto, forming a protective barrier between our solar system and the interstellar medium. The boundary of this sphere, called the heliopause, is where the pressure of the solar wind balances against the pressure of the interstellar gas and magnetic fields. Voyager 1 and 2 spacecraft have crossed this boundary into interstellar space, providing humanity's first direct measurements of this cosmic shoreline where the Sun's influence yields to the galaxy at large. A planetary nebula is the glowing shell of ionized gas ejected from a dying star. Despite their name, these beautiful, often symmetrical structures have nothing to do with planets. Early astronomers named them for their planet-like appearance through small telescopes. They represent a brief but spectacular phase in the life cycle of intermediate mass stars, when the star expels its outer layers into space, while its hot, exposed core illuminates the expanding gas shell, lasting only about 10,000 years, a mere blink in cosmic time. These nebulae display intricate structures, including rings, bipolar outflows, and complex patterns created by magnetic fields and binary companions, each a unique masterpiece of stellar demise. The Kuiper Belt is a disc-shaped region beyond Neptune containing icy bodies, extending from about 30 to 55 astronomical units from the Sun. This vast reservoir contains countless icy worlds, including Pluto, Haumea, Makemake, and Eris. These Kuiper Belt objects are pristine remnants from the solar system's formation, preserved in the deep freeze of the outer solar system. Their composition includes water ice, methane, and ammonia, and their orbits provide crucial clues about the early migration of the giant planets. The study of this region has revolutionized our understanding of the solar system's architecture and continues to reveal new classes of trans-Neptunian objects with unexpected properties and orbits. Solar prominences are enormous loops of plasma arching from the Sun's surface. These magnificent structures, anchored in the Sun's photosphere and extending hundreds of thousands of kilometers into the corona, are shaped by complex magnetic fields. While they appear dark against the bright solar disk when viewed in hydrogen alpha light, they glow brilliantly when seen against the darkness of space at the Sun's limb. These colossal features can remain stable for weeks or even months, containing plasma at temperatures around 10,000 Kelvin, cooler and denser than the surrounding corona, until they may suddenly erupt in spectacular coronal mass ejections that can send billions of tons of solar material racing across the solar system. The Hubble tension is a growing discrepancy in measurements of the universe's expansion rate. This modern cosmological puzzle arises from the disagreement between two precise methods of determining the Hubble constant, the rate at which the universe is expanding. Measurements based on the cosmic microwave background from the early universe conflict with measurements using Cepheid variables and supernovae in the nearby universe. The difference, while seemingly small statistically, persists despite increasingly precise measurements, suggesting the possibility of new physics beyond our current standard cosmological model, potentially involving dark energy, neutrinos, or other unknown components or interactions in the cosmic inventory. A Cepheid variable is a type of star whose regular pulsations provide a cosmic yardstick. These luminous yellow supergiants pulsate with remarkable regularity, brightening and dimming over periods ranging from days to months. The crucial discovery made by Henrietta Swan Leavitt in 1912 established that the period of these pulsations is directly related to their intrinsic luminosity. This period, luminosity, relationship, transforms Cepheids into standard candles. Once astronomers measure the pulsation period, they know the star's true brightness, and by comparing this to its apparent brightness from Earth, they can calculate its distance with excellent precision. This breakthrough provided the first reliable method for measuring distances to other galaxies and revealed the true scale of the universe. The Drake equation is a probabilistic formula estimating the number of communicative civilizations. Proposed by astronomer Frank Drake in 1961, this conceptual framework organizes the question of extraterrestrial intelligence into a series of factors: the rate of star formation, the fraction of stars with planets, the number of habitable planets per system, the fraction where life develops, the fraction where intelligence evolves, the fraction that develops detectable technology, and the length of time such civilizations release detectable signals. While most factors remain unknown, the equation provides a structured way to think about the enormous uncertainties in the search for extraterrestrial intelligence and highlights which parameters future research might constrain. A Type 1. A supernova results from the thermonuclear explosion of a white dwarf star. These tremendously luminous events occur in binary systems, where a white dwarf accretes material from a companion star until it reaches the Chandrasekhar limit of about 1.4 solar masses. At this critical threshold, the intense pressure and temperature trigger runaway carbon fusion, completely disrupting the white dwarf in a cataclysmic explosion. Because this mass limit is always the same, Type Ia supernovae always reach nearly the same peak luminosity, making them superb standard candles for measuring cosmic distances and crucial tools for discovering the accelerating expansion of the universe driven by dark energy. Cosmic rays are high-energy particles traveling through space at nearly light speed. These subatomic particles, primarily protons and atomic nuclei, originate from various astrophysical sources, including the Sun, supernova remnants, and active galactic nuclei. Carrying energies far beyond what human-made particle accelerators can produce, they constantly bombard Earth's atmosphere, where they collide with atoms to create cascading showers of secondary particles. The highest energy cosmic rays are among the most energetic phenomena in the universe, though their exact acceleration mechanisms remain mysterious. Their study provides insights into particle physics under extreme conditions and the violent processes occurring throughout the cosmos. The Gaia mission is creating an unprecedented three-dimensional map of our galaxy. This ambitious European Space Agency spacecraft is precisely measuring the positions, distances, motions, and properties of over 2 billion stars in the Milky Way. By repeatedly observing each star about 70 times over its planned mission, Gaia is revealing the galaxy's structure, formation history, and dynamic evolution with revolutionary precision. The data is uncovering stellar streams from disrupted dwarf galaxies, mapping the warped and flaring disk of the Milky Way, and providing crucial tests of cosmological models through local universe observations, essentially conducting a galactic archaeological dig through precise astrometry. A magnetar is a neutron star with an exceptionally powerful magnetic field. These extreme objects possess magnetic fields thousands of times stronger than ordinary neutron stars, reaching intensities of up to 10 to the 11th Tesla, quadrillions of times stronger than Earth's magnetic field. These fields are so powerful they can distort the electron clouds of atoms and have tangible effects on chemistry at a distance. Magnetars occasionally produce giant flares, releasing in 1 second more energy than our sun emits in 100,000 years, and can generate starquakes that crack their solid crusts, producing detectable ripples in space-time. They represent the upper limit of magnetic field strength possible in our universe. The local group is the galaxy cluster that includes the Milky Way. This gravitationally bound collection of more than 50 galaxies spans about 10 million light-years and is dominated by two large spiral galaxies, the Milky Way and Andromeda. The group also contains the Triangulum galaxy and numerous smaller dwarf galaxies, including the large and small Magellanic Clouds. All members are moving relative to each other, with the Milky Way and Andromeda on a collision course that will culminate in a merger billions of years from now. The local group itself is part of the larger Virgo supercluster, which is itself a component of the Laniakea supercluster. The Chandrasekhar limit is the maximum mass possible for a stable white dwarf star. Calculated by astrophysicist Subramanian Chandrasekhar at just 19 years old, this fundamental limit of approximately 1.4 solar masses represents the maximum mass that can be supported against gravitational collapse by electron degeneracy pressure. White dwarfs below this limit remain stable indefinitely, slowly cooling as black dwarfs. Those that accrete enough mass to exceed this limit, typically in binary systems, undergo catastrophic collapse and may explode as type I supernovae. This elegant result from quantum mechanics and relativity has profound implications for stellar evolution and the ultimate fate of most stars. A blazar is an active galactic nucleus with a jet pointed directly toward Earth. These extreme objects are a subclass of active galaxies where relativistic jets of plasma, powered by accretion onto a supermassive black hole, are aligned with our line of sight. This orientation creates several dramatic observational effects, including intense variability across the electromagnetic spectrum, apparent superluminal motion, and extraordinary luminosity. Blazars are among the most powerful persistent sources of gamma rays in the universe and serve as natural laboratories for studying particle acceleration to extreme energies and the physics of relativistic jets in the most violent environments known. The multiverse hypothesis suggests our universe may be one of many. This speculative but scientifically grounded concept proposes that what we call the universe might be just one region of a much larger and more complex meta-reality. Various versions of this hypothesis emerge from inflationary cosmology, string theory, and quantum mechanics, suggesting the possibility of countless other universes with different physical constants, dimensions, and laws of physics. While currently untestable and controversial, the multiverse concept represents a natural extension of several well-established physical theories and provides a potential context for understanding the apparent fine-tuning of our particular cosmic environment. The Great Attractor is a gravitational anomaly, pulling galaxies toward it. Located approximately 150 to 250 million light-years away in the direction of the Hydra Centaurus supercluster, this mysterious region of space exerts a gravitational influence so powerful that it pulls entire galaxy clusters, including our own Milky Way, toward it at velocities of several hundred kilometers per second. The precise nature of this cosmic attractor remains partially obscured by the zone of avoidance, the dusty region of our own galaxy that blocks our view, but appears to be associated with the Norma cluster, one of the most massive structures in our cosmic neighborhood. This immense gravitational pull reminds us that even on the largest scales, the universe is in constant, graceful motion, with vast flows of galaxies streaming along invisible gravitational pathways. Rogue planets are worlds that drift through interstellar space without orbiting a star. These lonely, dark wanderers may have formed around stars before being violently ejected by gravitational interactions, or they may have formed in isolation from collapsing gas clouds too small to become stars. Free from the warmth and light of a parent star, they travel through the cold emptiness of interstellar space, their surfaces frozen to temperatures only slightly above absolute zero. Some may possess thick atmospheres that trap internal heat from radioactive decay, potentially maintaining subsurface oceans where exotic forms of life might persist in complete darkness, forever isolated from the stellar communities that populate the galactic disk. Gravitational waves are ripples in the fabric of space-time, caused by accelerating masses. Predicted by Einstein's general theory of relativity and first directly detected in 2015, these waves are created by the most violent cosmic events, merging black holes, colliding neutron stars, and possibly the Big Bang itself. Unlike other forms of radiation, gravitational waves pass through matter almost completely unimpeded, carrying information about their cataclysmic sources across billions of light-years without distortion. Their detection has opened an entirely new window on the universe, allowing us to hear the cosmos in a way previously impossible and observe phenomena that emit little or no electromagnetic radiation. The Fermi paradox questions why we haven't detected evidence of extraterrestrial civilizations. Given the vast number of stars in our galaxy and the high probability that many harbor Earth-like planets, the apparent absence of detectable intelligent life presents a profound puzzle. Numerous solutions have been proposed. Perhaps technological civilizations are rare or short-lived. Maybe they develop in ways incomprehensible to us, or we might be looking for signals in the wrong way or at the wrong time. This paradox highlights both the specialness of our own existence and the profound mystery of whether we are alone in a galaxy that should, by statistical probability, be teeming with life. Galactic cannibalism occurs when larger galaxies merge with and absorb smaller ones. This process of hierarchical assembly is fundamental to galaxy evolution throughout cosmic time. Large galaxies grow by gravitationally capturing and eventually assimilating smaller satellite galaxies, tearing them apart into long streams of stars that wrap around the larger galaxy like cosmic spiderwebs. The Milky Way is currently consuming several dwarf galaxies, including the Sagittarius dwarf spheroidal, whose stars are being incorporated into our galaxy's halo. In billions of years, the ultimate act of galactic cannibalism will occur when the Milky Way and Andromeda galaxies merge to form a new, larger galaxy. The Hubble Deep Field revealed thousands of galaxies in a seemingly empty patch of sky. In 1995, astronomers pointed the Hubble Space Telescope at a dark, seemingly vacant area of space near the Big Dipper and collected light for 10 consecutive days. The resulting image, the Hubble Deep Field, revealed approximately 3,000 previously unknown galaxies in a region covering just 1/24 millionth of the entire sky. This profound observation demonstrated that the universe is filled with galaxies to the very limits of observation and provided a direct view back through cosmic time, showing galaxies as they appeared billions of years ago during their formative stages. Dark energy is the mysterious force driving the accelerated expansion of the universe. Discovered in the late 1990s through observations of distant supernovae, this enigmatic component constitutes about 68% of the total energy density of the universe. Unlike gravity, which pulls matter together, dark energy appears to cause space-time itself to expand at an accelerating rate. Its nature remains one of the greatest mysteries in physics. It might be a property of space itself, the cosmological constant, a dynamic field that changes over time, quintessence, or evidence that our understanding of gravity requires modification on cosmic scales. The cosmic microwave background is the remnant radiation from the early universe. This faint, nearly uniform glow permeates all of space, representing the oldest light we can observe, a snapshot of the universe when it was just 380,000 years old. Before this time, the universe was so hot and dense that it was opaque to light. As it expanded and cooled, neutral atoms formed, allowing photons to travel freely through space. These same photons, now redshifted by the expansion of the universe into the microwave part of the spectrum, provide the most compelling evidence for the Big Bang and reveal subtle density fluctuations that would eventually grow into the galaxies and large-scale structure we see today. Hypervelocity stars travel at speeds sufficient to escape the galaxy entirely. These rare, rapidly moving stars are thought to be created through gravitational interactions with the supermassive black hole at the galactic Wadley center, where a binary star system passes too close and one star is captured while the other is flung outward at tremendous speed. Some may also be accelerated through supernova explosions in binary systems or through interactions in dense star clusters. Traveling at over 1 million miles per hour, these stellar exiles are destined to leave the Milky Way and spend eternity wandering the intergalactic void, solitary travelers between the islands of light that make up the local galaxy group. The heat death of the universe is a theoretical end scenario. According to this hypothesis, the universe will eventually reach a state of maximum entropy where all energy is evenly distributed and no thermodynamic work can be performed. Stars will exhaust their nuclear fuel and cease shining. Black holes will slowly evaporate via Hawking radiation, and matter itself may decay into subatomic particles. The universe would become cold, dark, and increasingly dilute, with temperatures approaching absolute zero. This represents the ultimate fate in a scenario where the universe continues expanding indefinitely, a quiet, gradual conclusion to the cosmic story that began with a hot, dense Big Bang. A standard candle is an astronomical object with known intrinsic luminosity. These crucial distance measuring tools include Cepheid variable stars, R Lyrae stars, and Type 1a supernovae, all of which have relatively predictable brightnesses. By comparing an object's known intrinsic luminosity with its observed apparent brightness, astronomers can calculate its distance using the inverse square law. The establishment of reliable standard candles was fundamental to determining the scale of the universe, proving the existence of other galaxies beyond the Milky Way, and discovering the accelerating expansion of the universe driven by dark energy. The zone of avoidance refers to the area of sky obscured by the Milky Way. This band around the celestial equator, comprising about 20% of the night sky, is difficult to observe at optical wavelengths because of the light absorption and scattering caused by dust and stars in our own galaxy's plane. This obscuration has historically limited our knowledge of the large-scale structure of the universe in these directions, though modern observations in infrared, radio, and X-ray wavelengths are increasingly penetrating this zone, revealing previously hidden galaxies and helping complete our map of the cosmic web. A stellar stream is a linear structure of stars orbiting a galaxy. These graceful, arching formations represent the remnants of dwarf galaxies or globular clusters that are being tidally disrupted and stretched along their orbital paths by their host galaxy's gravity. The Sagittarius stream, for example, wraps around the Milky Way and represents the ongoing destruction of the Sagittarius dwarf elliptical galaxy. These stellar streams serve as fossil records of galactic assembly, preserving information about their parent systems and providing sensitive probes of the galactic gravitational potential, including the distribution of dark matter. Quantum fluctuations in the early universe seeded all cosmic structure. The microscopic random variations in energy density that existed during the inflationary epoch were stretched to astronomical scales by the rapid expansion of the universe. These tiny primordial irregularities, visible as minute temperature variations in the cosmic microwave background, created the gravitational seeds around which matter would eventually cluster, forming the first stars, galaxies, and the large-scale cosmic web. Thus, the entire structure of the observable universe, every galaxy, star, and planet, originated from quantum mechanical fluctuations smaller than a proton during the universe's first moments. The anthropic principle distinguishes between weak and strong interpretations. The weak anthropic principle simply notes that we observe the universe to be compatible with our existence as observers. We couldn't observe a universe incompatible with life. The strong anthropic principle suggests the universe must have properties that allow life to develop at some stage. While sometimes controversial, these principles provide a framework for discussing why the fundamental constants of nature appear finely tuned for complexity and life, whether through selection effects in a multiverse, cosmological natural selection, or other mechanisms we have yet to discover. A Lyman alpha blob is a huge concentration of hydrogen gas emitting Lyman alpha radiation. These enormous, faint structures, some measuring hundreds of thousands of light years across, represent reservoirs of primordial gas that are either cooling to form galaxies or being illuminated by intense star formation or active galactic nuclei. Most prevalent in the early universe, around 2 to 3 billion years after the Big Bang, they represent important phases in galaxy formation and evolution, potentially showing how the intergalactic medium fuels the growth of galaxies and how feedback processes regulate star formation throughout cosmic history. The holographic principle suggests the universe may be a projection from a lower dimensional boundary. This radical concept, emerging from the study of black hole thermodynamics and string theory, proposes that all the information contained within a volume of space can be represented as a hologram, encoded on a boundary to that region. If correct, this would mean our apparently three-dimensional reality might be a projection from information stored on a two-dimensional surface at the cosmic horizon, fundamentally challenging our understanding of space-time and information, and potentially providing a path toward reconciling gravity with quantum mechanics. A circumplanetary disk is a ring of gas and dust orbiting a young planet. Similar to how the early sun was surrounded by a protoplanetary disk from which planets formed, young giant planets are often encircled by their own disks of material from which the moons can form. Observations of these systems, particularly around young stars like PDS-70, provide direct insight into the formation processes of satellite systems like Jupiter's Galilean moons. Studying these circumplanetary disks helps astronomers understand the final stages of planet formation and the emergence of complex planetary systems with multiple moons. The Shapley supercluster is the largest concentration of matter in our local universe. Located about 650 million light-years away in the constellation Centaurus, this massive overdensity contains dozens of galaxy clusters and represents the greatest gravitational influence in our cosmic neighborhood. Even more significant, than the Great Attractor. The Milky Way, along with the entire Local Group and Virgo supercluster, is falling toward the Shapley supercluster as part of the bulk flow of galaxies on the largest scales, demonstrating how cosmic structures continue to evolve and assemble even today. Olber's paradox asks why the night sky is dark if the universe is infinite and filled with stars. Named after Heinrich Wilhelm Olbers, this centuries-old paradox notes that in an infinite, eternal universe with uniformly distributed stars, every line of sight should eventually terminate at a star, making the night sky uniformly bright. The resolution involves multiple factors. The finite age of the universe means light from the most distant stars hasn't reached us yet. The expansion of the universe redshifts starlight out of the visible spectrum, and the universe simply doesn't contain enough energy in starlight to create a bright sky. This simple question ultimately leads to profound insights about the nature and history of the cosmos. The cosmic web's filaments are highways of galaxy migration. These vast dark matter structures serve as the primary channels along which galaxies travel throughout cosmic time. Studies of galaxy motions reveal coherent flows of thousands of galaxies moving together along these invisible pathways, creating rivers of matter on scales of hundreds of millions of light years. These cosmic currents represent the continuing growth and evolution of the large-scale structure of the universe, with galaxies streaming toward the densest regions where clusters and superclusters continue to accumulate mass through these graceful, slow-motion flows that have persisted for billions of years. Neutron star mergers are cosmic forges of heavy elements. When two neutron stars spiral together and collide, they create some of the most energetic events in the universe, known as kilonovae. These collisions forge enormous quantities of heavy elements through rapid neutron capture processes, producing gold, platinum, uranium, and other precious metals that are then scattered into space. A single neutron star merger can create more than the mass of Earth in gold alone, seeding the interstellar medium with the materials that will eventually form new generations of stars and planets, and ultimately the elements that make up our jewelry and technology. The Hubble tension represents a growing crisis in cosmology. The discrepancy between measurements of the universe's expansion rate from the early universe using the cosmic microwave background and the modern universe using Cepheid variables and supernovae has now reached statistical significance that cannot be easily dismissed. This tension suggests either unknown systematic errors in our measurements, or more excitingly, the need for new physics beyond our current standard cosmological model. Potential solutions include early dark energy, new neutrino properties, or modifications to our understanding of gravity, making this one of the most active and important areas of contemporary cosmological research. Galactic archaeology reconstructs a galaxy's history through its stars. By studying the chemical compositions, ages, and orbital characteristics of millions of individual stars, astronomers can piece together the formation history of galaxies like our Milky Way. This stellar archaeology reveals evidence of past mergers with smaller galaxies, the timing of different star formation episodes, and the chemical enrichment history of the galactic environment. The Gaia mission, in particular, has revolutionized this field, providing precise three-dimensional motions and chemical fingerprints for over 2 billion stars, essentially allowing us to read our galaxy's autobiography written in the language of stellar properties. The first stars in the universe were likely enormous and short-lived. These population 3 stars, composed purely of hydrogen and helium with no heavier elements, probably formed with masses hundreds of times that of our Sun. Their immense size led to incredibly high core temperatures and pressures, causing them to burn through their nuclear fuel in just a few million years before ending their lives in spectacular pair instability supernovae that completely disrupted the star, leaving no remnant. These first stars began the process of cosmic chemical enrichment, forging the first heavy elements that would enable the formation of subsequent generations of smaller, longer-lived stars. The intergalactic medium contains most of the ordinary matter in the universe. This diffuse, highly ionized gas that fills the space between galaxies represents the majority of baryonic matter, though it's so thin, typically less than 1 atom per cubic meter, that it's incredibly difficult to detect. Studies using absorption lines in quasar spectra reveal this material is organized in a complex network of filaments and sheets that trace the cosmic web, with temperatures ranging from warm 10,000 Kelvin to hot 10 to 100 million Kelvin in different regions. Understanding this reservoir is crucial for completing the senses of ordinary matter in the universe. Gravitational lensing can create multiple images of the same astronomical object. When light from a distant galaxy or quasar passes near a massive foreground object like a galaxy cluster, the space-time curvature can bend the light rays along different paths, creating multiple images of the same background source. In special alignment cases, this produces complete or partial Einstein rings, beautiful circles of light surrounding the foreground lens. These cosmic mirages not only provide striking visual demonstrations of general relativity, but also serve as natural telescopes, magnifying distant objects that would otherwise be too faint to study in detail. The Gaia sausage is the remains of an ancient galaxy merger with the Milky Way. This distinct population of stars discovered in Gaia data represents the debris from a massive dwarf galaxy that collided with the Milky Way approximately 8 to 11 billion years ago. The stars from this merger, known as Gaia Enceladus, move on highly radial orbits that give them a sausage-like distribution in velocity space and contribute significantly to the Milky Way's inner halo. This dramatic accretion event likely delivered a substantial fraction of the Milky Way's stellar halo and may have triggered significant star formation in the early galaxy. Fast radio bursts are millisecond duration pulses of radio waves of unknown origin. These extremely energetic events, first discovered in 2007, release as much energy in 1,000th of a second as the Sun emits in 3 days. While most appear to be one-time events, some sources repeat, enabling astronomers to pinpoint their host galaxies. Leading theories for their origins include magnetar flares, merging compact objects, and other extreme astrophysical phenomena. Their study provides insights into the distribution of matter in the universe as the signals are dispersed by intervening electrons, allowing measurements of the cosmic web's baryon content. The solar system moves through the galaxy at about 230 kilometers per second. Our entire planetary system orbits the galactic center approximately 26,000 light-years away, completing one revolution every 225 to 250 million years, a period known as a cosmic year. During this journey, the solar system also oscillates above and below the galactic plane with a period of about 60 million years, potentially influencing Earth's climate and cosmic ray flux over geological timescales. This complex motion through different galactic environments reminds us that our position in the cosmos is constantly changing, even on human timescales. The circumstellar habitable zone depends on stellar type and evolution. The region around a star where liquid water could potentially exist on a planet's surface varies dramatically with the star's temperature and luminosity. Cool red dwarfs have habitable zones very close to the star, while hot, massive stars have habitable zones much farther out. Furthermore, as stars evolve and brighten over their lifetimes, their habitable zones migrate outward, meaning a planet that starts in the habitable zone may not remain there indefinitely. Understanding these dynamics is crucial for assessing the long-term potential habitability of exoplanets. Quantum gravity theories attempt to unify general relativity with quantum mechanics. This long-sought unification represents one of the biggest challenges in theoretical physics, with several competing approaches including string theory, loop quantum gravity, causal dynamical triangulation, and asymptotically safe gravity. Each approach offers different insights into the nature of space-time at the smallest scales, potentially explaining what happens at the center of black holes and during the Big Bang singularity. While experimental tests remain extremely challenging, the detection of primordial gravitational waves or unexpected features in high-energy particle collisions might provide crucial evidence. The epoch of Rayonization marked the universe's last major phase transition. Beginning about 400 million years after the Big Bang and lasting several hundred million years, this period saw the neutral hydrogen that filled the universe become ionized by the first stars, galaxies, and quasars. This Rayonization process cleared the cosmic fog that had previously made the universe opaque to ultraviolet light, creating the transparent intergalactic medium we observe today. Understanding this epoch is a major goal of upcoming telescopes, like the James Webb Space Telescope, which will observe the first galaxies that drove this cosmic transformation. Stellar mass black holes form from the collapse of massive stars. When stars more than about 20 to 25 times the mass of the Sun exhaust their nuclear fuel, their cores collapse catastrophically into black holes, typically ranging from about 5 to 50 solar masses. The recent detection of gravitational waves from merging stellar mass black holes has revealed populations with unexpected mass ranges, suggesting either different formation channels or previously unknown aspects of stellar evolution. These black holes can continue to grow by accreting material from companion stars in binary systems, creating bright X-ray sources throughout the galaxy. The cosmic distance ladder has multiple overlapping rungs for cross-verification. Modern cosmology employs numerous independent methods for measuring cosmic distances, including parallax for nearby stars, Cepheid variables, and RR-Lyrae stars for galactic distances, the Tully-Fisher and Faber-Jackson relations for galaxy distances, Type Ia supernovae for cosmological distances, and the cosmic distance ladder's highest rungs using galaxy redshifts and the cosmic microwave background. The consistency between these different methods provides confidence in our measurement of the universe's expansion history and helps identify potential systematic errors in any single approach. The lithium problem concerns the discrepancy between predicted and observed lithium abundances. Standard Big Bang nucleosynthesis predicts specific abundances of light elements, and while hydrogen, helium, and deuterium measurements generally match predictions, the observed lithium abundance in old stars is about 3 times lower than expected. This discrepancy suggests either incomplete understanding of stellar astrophysics, how stars process lithium, unknown nuclear reaction rates, or potentially new physics during the Big Bang. Solving the lithium problem remains an important test of our understanding of both stellar evolution and early universe cosmology. Galactic fountains cycle gas between the disk and halo of galaxies. When multiple supernovae explode in star-forming regions, they can create superbubbles that blow out of the galactic disk, lifting hot, metal-enriched gas high into the galactic halo. This gas then cools, condenses into clouds, and falls back onto the disk in a process resembling a fountain. This circulation enriches the interstellar medium with heavy elements produced in supernovae and regulates future star formation by redistributing gas throughout the galaxy. Similar processes likely operate in all star-forming galaxies, influencing their chemical evolution over cosmic time. The information paradox concerns the fate of information that falls into a black hole. According to quantum mechanics, information cannot be destroyed, but according to general relativity, anything that crosses a black hole's event horizon is lost forever from the outside universe. This contradiction represents one of the most fundamental unsolved problems in theoretical physics. Potential solutions involve information being encoded in the Hawking radiation emitted by black holes, being preserved on the event horizon, or requiring modifications to our understanding of quantum mechanics or gravity in extreme conditions. The WOW signal remains astronomy's most famous potential SET-I detection. Detected on August 15, 1977, by the Big Ear radio telescope at Ohio State University, this strong, narrow-band signal lasted for 72 seconds and matched the expected signature of an artificial extraterrestrial transmission. Despite numerous follow-up observations and investigations over decades, the signal was never detected again, and no satisfactory natural explanation has been confirmed. While most astronomers consider a terrestrial or natural origin more likely, the wow signal continues to inspire both scientific investigation and public fascination with the search for extraterrestrial intelligence. The simulation hypothesis proposes our universe might be a computational simulation. This philosophical concept, which has gained attention in scientific circles, suggests that advanced civilizations might create simulations of universes so detailed that the simulated beings within them would be conscious. If such simulations are possible and common, we might statistically be more likely to be in a simulation than in base reality. While currently untestable, some have proposed potential signatures of living in a simulation, such as fundamental resolution limits in space-time or anomalies in cosmic ray distributions. The hypothesis raises profound questions about the nature of reality and consciousness. Gravitational wave astronomy has opened a new window on the universe. The detection of ripples in space-time by LIGO and Virgo collaborations has initiated a new era of multi-messenger astronomy, where cosmic events can be observed through both light and gravitational waves. These observations have confirmed the existence of stellar mass black hole binaries, revealed unexpected populations of black holes, provided new measurements of the Hubble constant, and enabled tests of general relativity in extreme gravitational fields. Future space-based detectors will observe lower frequency gravitational waves from merging supermassive black holes, potentially revealing the cosmic history of galaxy mergers. The cosmic neutrino background permeates all of space, created just 1 second after the Big Bang, when the universe cooled enough for neutrinos to decouple from other matter. This relic background should fill the universe with approximately 336 neutrinos per cubic centimeter per flavor. Unlike the cosmic microwave background photons, these neutrinos have proven extraordinarily difficult to detect directly due to their extremely low energies and weak interactions with matter. Their detection would provide a snapshot of the universe at 1 second old, offering crucial information about the early universe and neutrino properties. Tidal disruption events occur when stars are torn apart by black holes. When a star wanders too close to a supermassive black hole, the intense tidal forces can rip the star apart in a spectacular display known as a tidal disruption event. About half of the stellar material is ejected from the system, while the rest forms an accretion disk around the black hole, producing a bright flare of radiation that can outshine the host galaxy for months. These events provide unique opportunities to study otherwise dormant black holes and the physics of accretion under extreme conditions, while also serving as laboratories for testing general relativity. The galaxy luminosity function describes the distribution of galaxy brightnesses. This fundamental statistical tool characterizes how many galaxies exist at different luminosity levels, revealing important information about galaxy formation and evolution. The function typically follows a Schechter function distribution with an exponential cutoff at high luminosities and a power law behavior at faint luminosities. Measurements of how the luminosity function evolves with redshift provide crucial constraints on models of galaxy evolution, showing how galaxies have grown and assembled their stars throughout cosmic history and how different populations, spirals, ellipticals, dwarfs, have changed over time. The Kardashev scale classifies civilizations by their energy utilization. Proposed by Russian astrophysicist Nikolai Kardashev, this hypothetical scale categorizes technological civilizations based on their energy consumption. Type 1 harnesses all available energy on their home planet, approximately 10 to the 16th power watts. Type 2 controls the energy output of their star, approximately 10 to the 26th power watts. And Type 3 commands the energy of an entire galaxy, approximately 10 to the power of 36 watts. While purely speculative, this framework provides a useful way to think about the potential capabilities of advanced civilizations and what signatures their activities might produce that could be detectable across interstellar distances. The BAO feature serves as a standard ruler for measuring cosmic expansion. Baryon acoustic oscillations are frozen sound waves in the distribution of galaxies, originating from pressure waves that traveled through the early universe's plasma before atoms formed. These oscillations imprint a preferred scale of about 490 million light-years in the clustering of galaxies, which appears as a small excess of galaxy pairs separated by this distance. Because the physical size of this standard ruler is known from early universe physics, measuring its apparent size at different redshifts provides a powerful probe of the universe's expansion history and the properties of dark energy. The triple alpha process creates carbon in stellar interiors. This two-step nuclear reaction, occurring in the cores of red giant stars, converts helium into carbon through the brief formation of unstable beryllium-8. The process requires precise conditions, specific temperatures and densities, and depends sensitively on the fundamental constants of nature. The existence of a resonant state in carbon-12 that enhances this reaction rate represents a famous example of apparent fine-tuning in physics, as without this resonance, insufficient carbon would be produced to support carbon-based life. This process also continues to produce oxygen and heavier elements through additional alpha particle captures. The galaxy halo connection links visible galaxies to their dark matter halos. In the modern paradigm of galaxy formation, every galaxy resides within an extended halo of dark matter that dominates its mass and gravitational potential. The properties of galaxies, their masses, sizes, morphologies, and star formation rates correlate with the properties of their host dark matter halos. Understanding this galaxy halo connection through techniques like abundance matching and halo occupation distribution modeling represents a central goal of galaxy formation theory, linking the visible components we observe to the invisible dark matter scaffolding that governs cosmic structure formation. The cosmic time scales from Planck time to the present span over 60 orders of magnitude. From the Planck time, 10 to the power of negative 43 seconds, when quantum gravity effects dominated, through nucleosynthesis, minutes, recombination, 380,000 years, reionization, hundreds of millions of years, to the present day, 13.8 billion years, the universe has progressed through dramatically different physical regimes. Each epoch left its imprint on the cosmos, from the primordial element abundances forged in the first minutes to the cosmic microwave background, released at recombination, and the large-scale structure that grew from tiny quantum fluctuations. This vast sweep of cosmic history provides context for humanity's relatively recent appearance in the universe's timeline. The universe's ultimate fate depends on the nature of dark energy. If dark energy remains constant, a cosmological constant, the universe will continue expanding indefinitely, growing increasingly cold and dilute in a heat-death scenario. If dark energy strengthens over time, phantom energy, it could eventually tear apart all bound structures. First galaxy clusters, then galaxies, solar systems, planets, and eventually atoms themselves, in a big rip. Alternatively, if dark energy decays, the expansion could slow or reverse, potentially leading to a big crunch. Determining dark energy's true nature remains one of cosmology's most important goals, as it will determine the ultimate destiny of our cosmos. And so we reach the end of our journey through 100 cosmic facts. We have traveled from the quantum flicker of the first moments to the vast, dark, energy-driven expansion of the future. We have wandered through the silent nurseries of stars, witnessed the patient dance of galaxies, and traced the invisible architecture of dark matter that holds the cosmos together. Each fact is a single point of light in an infinite tapestry, a brief glimpse into the quiet, relentless workings of a universe that is both deeply strange and profoundly beautiful. The relentless expansion, the slow fusion in stellar hearts, the gentle gravitational pull between worlds. These are the rhythms of a cosmos that operates on scales of space and time far beyond human measure. There is a profound peace in this scale. The universe continues its slow, elegant processes, regardless of our daily worries or fleeting thoughts. It is a reminder that rest is not just a human need, but a fundamental state of being in a cosmos where even the most violent events occur in perfect silence, and where the longest journeys end in quiet dissipation. The atoms that form your body have already completed epic voyages across space and time. They have been forged in stellar furnaces, scattered by supernovae, and gathered into the planet you call home. Now, for this brief moment, they have assembled into a form that can contemplate the very cosmos that created them. And now, that form can rest. Let the vast, dark quiet of space become your quiet. Let the slow, patient turning of galaxies become the rhythm of your breathing. Let the knowledge that you are and always have been a part of this magnificent cosmos ease you into a deep and peaceful sleep. The stars will keep their watch, the universe will continue its expansion, and you can release the day, drifting into the same cosmic dark that cradles every world, every star, every silent drifting atom. Good night.